got a little crowded here, and I know that only my wife is here because of my pretty eyes. Most of you are probably here because the title of the talk seems interesting, so I guess it means some of you are dealing with these issues. So I'm Ofri Raviv. I'm a data scientist in PayPal, working at the Tel Aviv site. The site was founded about 10 years ago. We have more than 200 employees currently, most of which are dealing with data science and risk prevention. Some are also software developers and smaller business unit doing regional sales and marketing. So what I want to talk about today is how do we handle imperfectly labeled data. And I'm going to present a methodology that was briefly mentioned by Professor Zaria's keynote that helps us do that. So like most of you in this room, I guess we are in the business of building machine learning models. One of the key components in building machine learning models is the data. In the context of supervised machine learning, the data can take the form of a big matrix where each row is a specific example and each column corresponds to the values of one feature for all of the different columns, for all of the different examples. Now, we also have one special column of the labels. Now, the labels represent what we are trying to teach the model, what the desired output for every example is. And importantly, we usually tend to assume that the labels are perfect, that we can come up with completely accurate labels. Now, in some domains, this makes sense. Like if you're building an ad click prediction algorithm, then you show some ads to some users, and you measure which user clicked which ad, and you have pretty close to perfect data. But if your problem is different, if you're trying to, for example, build a machine learning model that is supposed to look at a radiological scan and tell you whether a tumor is present in the scan, then your labels probably come from some human radiologist looking at the same scans and labeling them. And even the best radiologist doesn't have 100% accuracy, so your labels necessarily have some amount of noise in them. So let me tell you a little bit about our use case. So PayPal, as you all know, enables people to pay over the internet. Fraudsters, that's our term for the internet's bad guys, they try to steal money from PayPal's users. And they try to do that in several different ways. I'm going to talk about one of them, which is something we call unauthorized transactions. It starts when a fraudster gets a hold of a legitimate user's credentials, username and password. How do they do that? One possible way is through phishing. Like the email that you see here, they send an email pretending to be from PayPal to basically random emails saying something like immediate action required, log into your account now, otherwise we will disable it, or something like that. Now, most of the users who get these emails realize this is a scam, but some people don't. And they click the link and they don't notice that they're actually not in the real PayPal website, but in a fake website, and they try to log in, actually providing their credentials to the fraudster. Now, the fraudsters take these credentials and log into the real PayPal website and make some transaction on behalf of the user. For example, transfer $200 from the user's account to the fraudster's account. Now, sometime afterwards, the user notices a suspicious transaction, a transaction they don't know anything about. So they log into their PayPal account and they report the unauthorized transaction. In our terminology, they file a claim saying this transaction was not authorized by me. Now, this claim gets sent to a customer support representative that is specifically trained to deal with this kind of issues. The customer support rep reviews the claim, the transaction, the user's account, all of the information related to it, and decides whether to approve the claim. And if they approve the claim, then we issue a refund to the user. Now, we don't like it when this happens, right? First, because we lose money, but more importantly, because this is a bad user experience. We want our users' accounts to be safe, even if they made a mistake like responding to that phishing email. So what do we do about that? We train machine learning models to look at the transactions in runtime and classify them as good or bad. In this context, good means a transaction being made by the legitimate account owner, and bad means a transaction being made by fraudster. So how do we train these models? Well, we have a lot of data, a lot of historical data about previous transactions by many users. For every transaction, we have many features. So like the amount of the transaction, the time of day, how consistent is the time of day with previous purchases by the same user, and so on. Many features, thousands of features actually. And at runtime, after we train this model, the model runs and looks at all of the features of the transaction and decides whether it looks like a good or bad transaction. And if it's a bad transaction with high enough certainty, then we actually block the transaction. And okay, so now going back to the labels, where do we come up with the labels? So we assume that all of the transactions are good unless someone filed a claim related to that transaction and the claim was approved, right? Seems pretty simple. So what's the problem here? So every once in a while, before we start an iteration of working on improving the performance of the model, we do something we call gap analysis. So we compare the predictions of the model here with the labels. So the vast majority of the traffic of the transactions is going to be here. Okay, so good users that were classified by the model is good. Everyone's happy. Some of the traffic is going to be here. It's a fraudulent transaction or an unauthorized transaction that was identified as unauthorized by the model. Everyone's happy except for the fraudster, but that's also good. But what we usually do is we take a test set of transactions and we dive into these buckets, the false alarms and the misses. And we do that because if you review enough cases, you can actually come up with leads. If you understand what went wrong, why was the model wrong, you can derive leads to the next version and the next iteration of the model. And what happened in a recent gap analysis is that we started reviewing these cases, but we found ourselves agreeing with the model more often than with the label. So that made us realize that unlike what we used to think, the population of bad transactions and the population that is labeled as bad are not entirely the same. They have some differences. And we started diving into this and we found some explanations for the differences. I'll only mention 3 examples. So one pretty simple difference comes from the fact that not all of the users report all of the transactions. So if a transaction was bad, but it was never reported, then we will not know that it's bad. It won't be labeled as bad in our data set. On the other hand, we have transactions that are labeled as bad in our data set, but are not really bad. So, one example is something we call goodwill. So this customer support representative reviewed the case, decided there was no unauthorized transaction here, but out of goodwill, they're going to issue a refund anyway. For example, so maybe the user made a transaction and forgot about it and something like that. They actually have guidelines on when they are, if it's the user has been with PayPal for a very long time and the amount is not so big and so on, they may actually issue a refund anyway, even though they realize there was no unauthorized transaction. Another similar but slightly different issue is something called item dispute. So if the user purchased something through PayPal and didn't receive the item, PayPal also issues a refund. But technically, the user was not supposed to file an unauthorized transaction claim. He was supposed to file a different type of claim. But users make mistakes, obviously, and the customer support rep that reviewed the case was supposed to change the type of the claim, but again, they don't always do that. They're more focused on the outcome to the user and not on us, the data scientists. So we end up with slightly dirty labels in our data set. So all of that made us realize that we need better labels. Or alternatively, we need a way to handle the fact that our labels are not entirely accurate. So how can we do that? The textbook approach would tell us, okay, throw away all of the dirty labels that you have, hire a bunch of analysts, train them really well so they hardly make any mistakes at all, and then let them manually label each and every transaction, telling you whether it was good or bad, and then use that as the training set for your model. Now, fine, that's good for the textbook. In our use case, that would be unrealistically expensive to do that, to review every transaction. Okay, it doesn't scale at all. So another approach that I think there was a workshop about it here yesterday is called active learning. So the main idea of active learning is still uses manual labeling, but instead of doing it for all of the data set, instead of manually labeling all of your examples or a random subset of the data set, you try to come up with smart ways to figure out which are the most informative examples to label, to send to the analysts to labeling. We actually have some projects using active learning. We have some very good experience with it. It improves the scalability by a lot. So it could be something like a factor of 10 over randomly labeling examples. But still, in our use case, that was not good enough. It still doesn't scale to the amount of transactions that we have that we need to label in order to train our models. So another approach that does scale really well is something called semi-supervised learning. So semi-supervised learning is a class of algorithms designed to benefit both from labeled data and unlabeled data. Okay? There are examples out there of really high-scale semi-supervised learning implementations. But the problem with this approach was that it didn't really let us utilize the fact that we already have labels for almost everything. They're not entirely accurate labels, but we do have labels. So we wanted to utilize that. We didn't want to throw them away. And in semi-supervised learning, every example is either labeled perfectly, implicitly assume it's perfect, or it's unlabeled, completely unlabeled. We don't know anything about it. So this approach, we didn't take this approach because of that issue of not leveraging the existing labels. So that led us to try to look harder, and we came up, we found this approach called weak supervision. So weak supervision was actually, weak supervision, and specifically something called data programming, was introduced in NIPS 2 years ago by Professor Christopher Ray's lab in Stanford. And the gist of it is this. So every example has a true label. It's either good or bad, but we don't know that. Only the gods know the true label of the transaction. What we do know, we model as labeling functions. We can have many labeling functions. Each labeling function is a function that takes as input a transaction, and as the output, it either labels this example as positive or negative, or it can abstain. It can also output 0 as a way to abstain, to say, I don't know how to classify this specific example. So you can think about it as if we're taking what we used to have as the label, our only label. If the transaction has an approved unauthorized claim, it's bad. And we're not assuming that this is the label. This is a label. This is one labeling function. Then we develop more labeling functions. For example, we can take what I said about the item disputes issue that we discovered, and we can formulate this as another labeling function. For example, if we have an approved unauthorized claim, but the claim text contains the word damaged, then it's actually not a bad transaction in the sense of unauthorized, okay? In the sense of unauthorized transactions, it's actually good. The user is acknowledging the fact that he's the one who made the transaction, but he just didn't receive the item. and so on. We can develop many more labeling functions. How do we develop these labeling functions? So remember the analysts from before, the ones that you hire and let them label millions of transactions. So in this approach, we hire the analysts and we train them, but not to manually label millions of transactions, but to write heuristics, to write labeling functions. So that's where the scalability of this method comes from using the expensive human resource in a much more efficient manner. So after we've done that and we have many labeling functions, what we do is we use data to try to learn the accuracy of each of these labeling functions. When we have these accuracies of the different labeling functions, we can actually take an unlabeled example, observe what the different labeling functions tell us about what each of them estimates from its own perspective about the true label, and then we can combine all of this using a generative model to estimate the probability of the true label of this specific transaction, of this specific example. Then when we have that, we can train any kind of model that we want to do the runtime inference on this, to actually predict from the features that we have available, the amount and so on, whether it's going to be a good or bad transaction. Now, one can ask, why do we need two different models? At this point, after we've trained the generative model and we have an estimate of the probability of the transaction being good or bad, why can't we just use the output of this model? And let's say if the estimate of the model says higher than 5% of a bad transaction, then block the transaction. So there are actually two reasons why. First, you have to remember that the labeling functions can cheat, in the sense that labeling functions can use data that is not available at the moment of the transaction. Look at these examples of labeling functions. They look at the claim. The claim does not exist at the moment of the transaction. It will only exist for a small subset of the transactions a day later, a week later. So obviously we can't use that as the runtime model that is supposed to stop the bad transactions from happening in the first place. But we can use that to clean up the dirty labels in our training set, because when we train the model, we already have access to that data. So that's one reason. Another reason is that, remember that I said before, we have thousands of variables. Now, even the best analyst in the world doesn't know how to write labeling functions that take into account thousands of variables. So the analysts write simple labeling functions. These are actually realistic examples of labeling functions. They are supposed to be simple. They are supposed to be understandable by analysts or by domain experts. And they're not going to write labeling functions that look at complicated structures and complicated correlations between different features that we have in the data. That's what this model does, and you can actually use, in this methodology, you can use any type of machine learning model that you like, a deep neural network, a GBT, logistic regression, whatever you like. All right, so one of the main questions here is, how do we learn the different labeling function accuracies? So if we have access to enough gold label data, manually labeled with very high accuracy, it's pretty simple. We compare the output of each labeling function to the gold label, and we can directly measure its accuracy. But it turns out that we can actually do that even without gold labels. I'll try to give the gist of how this magic happens. You can, of course, read the papers for more detail. Right. This is going to be the technical slide of the talk. Okay, so how do we estimate the accuracies of the different labeling functions without access to gold labels? So think about it this way. Every labeling function is characterized by two parameters: a beta, which is the coverage, which captures what is the probability that this labeling function is going to not abstain, to give us a non-zero label for an example, and alpha I, which is the accuracy. Given that it labeled, what is the probability that it actually labeled correctly? Now, if we have n labeling function, then we have two n parameters, and if we know these two n parameters, we know everything there is to know about this model, everything there is to know about this joint probability of the true label and the different possible outputs of the labeling functions. So we can think of this big table is actually the joint distribution. If we put values, numerical values in here in the P column, then we're actually depicting the probability of every possible state of the world, the true probability being y, and the first labeling function being 1, sorry, and the first labeling function returning also 1, and so on. So it's actually not that complicated to figure out what is this probability in terms of alphas and betas. It's the expression given here. The details are not that important, but what is important that we can actually, so given a training set, unlabeled training set, what we can do is we can find the alphas and the betas that maximize the log likelihood of our observations, of the different labels that we have seen our labeling functions output for this training set. And it doesn't matter that we don't know the Y column, the true label column. We just sum over all the different possible values of the true label of every example, factoring in the relative probabilities of each possible true label. All right, so now to simplify things, I assumed in this explanation that the labeling functions are independent. That's actually a very bad assumption. As you've seen in the examples I presented before, they are going to be highly dependent, the labeling functions that we write. And it's very important to model these dependencies because it's going to affect our estimate of the probability of an example being good or bad. So it turns out that to evaluate the dependencies between different labeling functions, we can use a very similar methodology to what we've seen in the previous slide. Everything gets a little bit messier because we have many more parameters, and instead of just two parameters, alpha and beta, for every labeling function we have parameters describing, we have alpha and beta, but also parameters quantifying the correlation of every function to every other function. So it becomes much more difficult technically, but conceptually the same. And the main interesting question here is how many correlations do we want to model? It's basically a trade-off between the accuracy of the model. If we model all possible correlations and measure all of the possible correlations from the data, we have a very accurate model, but also a very complicated model that takes a long time to train and a long time to run the inference on. On the other hand, we can assume, for example, the other extreme, no correlations at all, basically the naive Bayes assumption, and then we will end up with a very simple model, but one that is probably less accurate. So just in practice, most people only model pairwise correlations between the functions, even though there could be more complicated, higher order correlations. In practice, I haven't seen anyone try to model them. There is no good mathematical reason behind this. It just seems to work nicely. And another important thing is that if you can, in advance, it doesn't matter from which source, if you can say that two functions are not going to be highly correlated, then you can ignore the correlation between them altogether because it's not going to affect your outputs very much. So if you can filter out the correlations somehow to only include in the model the strong correlations, you can save a lot of computation time and still gain the same accuracy. So I hope I've convinced you of two things by now. First of all, that this is something important to try to model the noise in your labels, and second, that it's a little bit complicated because there are a lot of details to consider and many algorithms to implement and so on. So it turns out that the good news is that the same research group from Stanford that advocates this approach actually also implemented something in Python, a Python package that is actually a working end-to-end solution to this weak supervision and data programming approach. It actually walks you through the process of defining labeling functions, evaluating their accuracies, the correlations between them, and then running the inference on the model to get some estimation of the true labels of your training set. They also have really nice tutorials you can follow in the as Jupyter notebooks, so you can learn quite easily how to work with it. But if you decide to use it, then just a few words. You have to remember that it's very research code. And more importantly, it's really geared towards a specific use case that this labs comes from, of extracting structured knowledge from unstructured text. So their typical example would be chemical disease relation extraction. So the input is all of the scientific papers in the biochemical journals, and the output would be this chemical is related to this disease. And this domain has many problems that are unique to it, to the fact that you don't start with a big matrix that we in this more structured data problem start from. So just a few words on where we are standing with this. We've been experimenting with Snorkel and generally the weak supervision approach. We've implemented a relatively small scale experiment. We're now moving on to a larger scale experiment, and inshallah, if everything works correctly, then we will have in a few months first model in production that was trained using this methodology, and maybe in the future adoption in other domains as well. So I hope by now I've convinced you that getting perfectly labeled data is difficult, or that if you chose to come to this presentation, then you probably knew that already. And so just acknowledging the fact that our labels may be somewhat inaccurate can go a long way and can start the journey of fixing these labels and coming up with the labeling functions, even if you don't end up implementing all of these algorithms and stuff. Just looking at not the label, but labels, and asking ourselves how accurate they are is a very, very important step forward. And specifically, even though there are many approaches to deal with how to get more labeled data or better labeled data, weak supervision is one less well-known approach that tries to model the noise in the labels instead of ignoring it. So I know I am the last thing standing between you and lunch, so I won't take any questions now, but I will be at the PayPal booth downstairs, so either come talk to me now or down at the booth. Thank you.